Okay, our first speaker is Eduardo Gonzalo Badia, who's going to tell us about constraints on the standard model from AdS conjectures. Take it away, Eduardo.
Thank you. Thank you. I'd like to first thank the organizers for giving me the opportunity to talk in this very nice series on string Feno. So today I'm going to talk about work with Luis Ibáñez and Irene Valenzuela. In particular, I'm going to talk a little bit about this paper that we put out in April, and then about a paper, upcoming work, which is more related to Feno and the standard model. So in the first part of my talk, I will introduce a new Swampland conjecture, which is the Light Fermion Swampland Conjecture, and I will motivate it by studying the non-supersymmetric AdS instability conjecture and the anti-de Sitter distance conjecture in generic setups in Minkowski, de Sitter, and anti-de Sitter. We will see later what I mean by this. And in the second part of my talk, we will use what we've learned from generic effective theories in arbitrary dimension. We will apply it to the standard model and try to put constraints on neutrinos and extract some phenomenology. So we start with an effective field theory in the dimensions, and we compactify in a circle. If the theory in D-1 is inconsistent, so it violates some Swampland conjecture, then we will assume that the original theory in D dimensions was itself inconsistent. Now, of course, this doesn't necessarily have to work for any conjecture or for any dimension, but we will assume that it does, at least for the conjectures that we will use today. So this criteria has actually been useful sometimes to test and refine conjectures. So we will assume that we have some massless particles in our spectrum, in our effective field theory. So let's say that we have the graviton, some gauge bosons, perhaps some massless fermions. And then we will call the total number of massless plus massive fermionic degrees of freedom NF and NB for the bosons. So pretty generic setup. The two conjectures that we study first, let me briefly review them, are the non-supersymmetric AdS instability conjecture, which tells you that non-supersymmetric AdS vacua must at best be metastable. And the second one is the anti-de Sitter distance conjecture, which, as we all know, tells you that when the cosmological constant goes to 0, some tower is supposed to become light to prevent this infinite distance limit. And in the mild version, we just assume that this tower comes down with a power alpha, which is positive and order 1 number. In the, let's say, strong version, it has to be precisely 1/2 for supersymmetric vacua. And in an, let's say, even stronger version, it has to be larger than 1/2 for non-supersymmetric vacua. And it should also hold in de Sitter with, in this case, alpha smaller than 1/2. So the idea is to find generic conditions on the spectra of the theory such that under dimensional reduction in a circle, the potential for the radion has an anti-de Sitter vacua. And then we make some assumptions so that this anti-de Sitter vacua should not appear, should not be there. So we want to forbid it. And if we want to forbid it with the non-AdS conjecture, then we need to assume that this vacua is non-supersymmetric and stable. It was shown in these works that Wilson lines can give rise to non-perturbative stabilities, but we will assume that they are either, let's say, killed by nucleation dynamics, or we take them away by orbifolding or something, so that we can have things to say. And if we use the anti-de Sitter distance conjecture, then just having an anti-de Sitter vacua is not a problem. We can only say things if this de Sitter vacua can go all the way into Minkowski, so the cosmological constant goes to 0 as we scan along some of the parameters in our theory, in this case, the masses of the particles. Okay, so this is the idea. Some formulas. Okay, so we compactify in a circle. We introduce the radion. We have no Wilson lines, and the effective potential for the radion will have a classical term, which is the dimensional reduction of the cosmological constant, and on top of which we'll compute some one-loop quantum corrections. The classical term will be positive if we started in de Sitter, negative if we started in anti-de Sitter, and it will vanish if we started in Minkowski. The quantum corrections will be positive for fermions, negative for bosons, and they will be exponentially suppressed with the masses of the particles. So we study, if we are studying the potential at a given scale, then all particles which are more massive, essentially they will not contribute to the potential. Okay, so this is the setup. Now, since we want to find constraints on the spectra that give rise to anti-de Sitter vacua, the idea of the reasoning goes as following. So we focus on the scale of the cosmological constant, and we want to see how the potential behaves in the ultraviolet limit and in the infrared limit with respect to the scale of the cosmological constant. So who dominates for scales which are much smaller than this scale? So in the UV with respect to the cosmological constant, so we can expand the formulas for the potential, and after summing over all degrees of freedom that are included in your effective field theory, so we assume that there's some gap, but after everything that's in your effective field theory, there's some gap to the rest of things, so that our results make sense, and we can do this supertrace, and it makes sense to do it. And then one finds that in the UV, the sign of the potential is determined by the first non-vanishing supertrace. So the potential is proportional to -1 to the k plus 1 times the first non-vanishing supertrace. So for k equals 0, this means that the potential is proportional to the number of fermions minus the number of bosons. If this is 0, then we have to go to the next level, and then the sign of the potential is determined by the supertrace of m squared, so by this formula right here. Now we ask who dominates in the infrared. So if there is a non-zero cosmological constant, then the sign of the potential will be given by the sign of the cosmological constant. But if we start in Minkowski, then it will be given by either it will be positive if we have more massless fermions than massless bosons, and even if we have a cosmological constant in the, let's say, in the middle, so between the IR and the UV, there will be a region which will be dominated by the massless sector. So if there's a surplus of massless fermions, then the potential will be positive. Otherwise, it will be negative, like say in the middle. Okay, so perhaps all of this was a little bit messy, but once now we come to the examples, it will become more clear. Okay, so we start with Minkowski, and we will always focus on the case where the first non-vanishing supertrace is positive, because this is what generates the anti-de Sitter vacua. So the potential is positive in the ultraviolet. Now in the infrared, it will go to 0 because we're Minkowski, but it will do so from below if the massless bosons dominate, and it will do so from above if massless fermions dominate. So it is in this case that 100% sure an anti-de Sitter vacua has to generate. Here it could be generated, but it could not be generated. So the first claim is that in Minkowski, with the first non-vanishing supertrace positive, we need a surplus of massless fermions. And in the standard model, we have 48 degrees of freedom from violet fermions and 12 gauge bosons. So the first condition is satisfied. So if neutrinos are massive, as indeed we know they are, then we could have said that cosmological constant could not be 0. So in a sense, it's like if neutrinos are massless, we could have predicted that we needed a non-zero cosmological constant, so that the lightest fermions in your theory can have a mass. If we study the other conjecture, the distance conjecture, then we find that the height of the potential, the depth of the potential cannot go to 0 unless the radion goes to infinity, in which case the Kaluza-Klein tower comes down. And it does so with the power 1/d on the cosmological constant. So regarding the anti-de Sitter distance conjecture, we find no disagreement under the study of dimensional reduction in a circle that we're doing, only with the stronger version of the conjecture, which requires that alpha is larger than 1/2. Now we move on to the Sitter. Again, in the UV, the potential is positive, and in the infrared, it will go to 0 from above, since we're in the Sitter. But in the middle, if we do not have light fermions, we do not have a surplus of light fermions, then the potential will become negative. And again, we will have this anti-de Sitter vacua. So the claim for de Sitter regarding the non-SUSY AdS conjecture is that if the first non-vanishing supertrace is positive, then we need to have enough light fermions. Of course, the de Sitter can be unstable as long as the anti-de Sitter vacua in one dimension less is stable. So this is an assumption that we are making. And we will see later, a little bit later, the particular implications for the standard model neutrinos. Now, if we study anti-de Sitter distance conjecture for de Sitter, we find that the potential can go to 0, even if R is not going to infinity. So at the finite value of R, it will do so. It will do it at the scale set by the masses of the lightest fermions in your theory. So if they are lighter than the cosmological constant, then the potential will not do this. It will just stop at some point. So somehow we say, okay, so way out is saying that when you embed this in string theory, the scanning will not be allowed. So that this scanning does not make sense, and that indeed the fermions can only be as heavy as the cosmological constant. So you need to have some light fermions. Of course, another possibility is that the fermions are part of the tower, so that they are indeed the tower, and then it can also be consistent. So those are the two options. Now, for anti-de Sitter, things are a little bit different, because in the infrared, the potential will go to 0 from below, since the cosmological constant was already negative. And in this case, even if we have massless fermions, we will always have an anti-de Sitter vacua. So the claim is that the first non-vanishing supertrace has to be negative, or the vacua has to be unstable, so that perhaps it was already unstable, and the instability transmits when you compactify a circle, or some new instability appears. Regarding the anti-de Sitter distance conjecture, it turns out that when you have a 3-level negative cosmological constant, you cannot scan all the way until the depth of the potential goes to 0, unless in the scanning you somehow change the cosmological constant. So the scans that we're making is we're just making the masses of the fermions, we just changing them, making them lighter. If we do that, then everything's fine, because the cosmological constant does not go to 0. It can only go to 0 if the cosmological constant, the classical cosmological constant in large D dimensions itself is going to 0 in this scan. But in this, if we do this, then already before the dimensional reduction, there has to be a tower there. In this case, the Caruso-Klein tower would come down with a power also 1/d. You can compute this. So anti-de Sitter vacua seem consistent with a mild, but not with a strong version. Okay, so conclusions for this first part. So supported by the non-supersymmetric AdS instability conjecture in de Sitter and Minkowski, and also from the anti-de Sitter distance conjecture in de Sitter. This is I'm trying to make a summary of the most important points. So with these 3 examples that we showed today, we can say that the result is actually more general, so that the assumptions that we were making, so that these 2 conjectures apply, that we can scan, and that we have some stability. So we say that there could perhaps be a deeper principle, which is the Light Fermion Conjecture, which tells you that in theories where with broken supersymmetry and positive or 0 cosmological constant and positive non-vanishing supertrace, then there has to be a surplus of light fermions. This is the proposal. Of course, it would be interesting to test it in non-supersymmetric de Sitter and Minkowski vacua in string theory. Best we could come up with so far is almost a test, which is the theoretic SO16 cross SO16, because in this theory, vacuum energy is positive, but we don't have a vacua. We have a runaway potential, so it's not. So the motivation is weaker, right? Because we started with these 2 conjectures, which require a vacua. but indeed the vacuum energy is positive, and you can compute the supertrace, and it turns out that it's positive. And when you look at the spectrum, you find that there is indeed this surplus of massless fermions. So we say this is almost a test, but it would be this is something we are interested to do in the future, to look for to test this conjecture, whether it is something more general or just some nice thing that happens that follows from the non-supersymmetric AdS stability conjecture and the anti-de Sitter distance conjecture. Perhaps it is something more general. Of course, it will be interesting to look for some perhaps heuristic argument of why light fermions seem to be required in pretty generic situations. Okay, in the next part of my talk, I'm going to focus on phenomenology. So I'm going to try to apply these ideas to the standard model. So in the standard model, neutrinos are massless, and we need to extend it in some way so that we can account for neutrino masses. And we want to test these extensions of the standard model because we want them to be in the landscape. This is the idea. So we will consider essentially two possibilities to do this. The first one is a case where neutrinos are Dirac, and then we add some sterile neutrinos so that in total we have 12 light degrees of freedom. The second possibility is the case of Modular Neutrinos, and in this case, depending on the relative strength of the Majorana mass and the Dirac mass, we will have somewhere between 6 and 12 light degrees of freedom. And interestingly, what we will see, so according to the ideas that are presented, quantum gravity wants in these setups to have light fermions. So CISO scenarios where we have only, so where the Majorana mass is much larger than the Dirac mass, and in this way you can explain why the active neutrinos are so light. Since we have only 6 light degrees of freedom, this leads to inconsistencies. Now we can say things not only about the nature, but also about the absolute scale and the ordering of the neutrinos, at least in principle. Finally, as a final motivation for this part, we ask, why do the scale of neutrino masses and dark energy coincide? So in this plot, I have here the mass of the heaviest neutrino, so the smallest mass that it can have according to neutrino oscillations. It's very close to dark energy scale. So this was already known that the standard model has 3D anti-de Sitter vacua, and they can be avoided if neutrinos are Dirac or pseudo-Dirac, and they have masses smaller than the cosmological constant. But like we've been seeing today, in order to obtain this nice result, you need to assume that these vacua are stable, and this requires UV information. So we check the other conjecture, which does not require UV information, which is the anti-de Sitter distance conjecture. And when you look at the equations in detail, you find that the position of the vacua and the depth depends on the masses of the neutrinos. The rest of the particles in the standard model do not contribute here because, like I said, their contribution is exponentially suppressed. So according to the conjecture, if in a certain direction of field space, so we can think like we're changing the BEF of the Higgs or the Yukawas of some neutrinos, the cosmological constant goes to 0, then some tower of state should become light. In this plot, we see how if we change the masses of the lightest neutrino from 9 millielectron volts to 6 millielectron volts, while so in this plot we are scanning along, we can think the BEF of the Higgs, so that all of the neutrinos are getting lighter. So we find that the vacua can go from de Sitter to anti-de Sitter, and it does so at a finite value of R, where you don't the Kaluza line scale is the Kaluza line tower is not coming loud, it's not coming down. Let's first review the assumptions that we're making. So first, we are assuming that there is a family of vacua, so that we can actually make this scan when we embed the standard model in string theory. The other assumption that we're making is that the scanning starts at the point where all neutrinos are massless, and it ends at the experimentally measured value for the masses. So when you do this in a little bit more detail, you find these plots. The left-hand side is for Majorana neutrinos, the right-hand side is for Dirac neutrinos, and we're trying to make a scan, like I said, from 0 to the experimental value. without crossing regions where we have no vacua, where we have de Sitter vacua, and where we have anti-de Sitter vacua. So it turns out that for modular neutrinos, we cannot do this. And for direct neutrinos, we can do it if the mass of the lightest fermion is smaller than 6.6 millielectron volts. To obtain the results, constraints from neutrino oscillations are actually essential. Now, one can argue, okay, so you obtain all of these results by scanning along the masses of the neutrinos, but what about the cosmological constant? Isn't it a strong assumption to assume that the BEF of the Higgs can change and the cosmological constant cannot change? So it's a good question, and it turns out that when you look at this in more detail, a second option arises, and it is that the cosmological constant goes to zero as we scan as the masses of the neutrinos go to zero. And so, in particular, if we consider yet another Swampland conjecture, which is the festina lente, which tells you that for every charged particle in the spectrum, its mass has to be larger than the cosmological constant, so that large charged black holes in the zero can evaporate. And one immediately sees that if let's say you think of the mass of the electron and the neutrinos both are scanning with the BEF of the Higgs, so proportional to lambda, they're going to zero, then festina lente requires that the lambda should change in this scan. So assuming the rest of the things here don't change in the scan. So a scanning that would be allowed is a scanning where the cosmological constant goes with lambda to the fourth or larger than fourth, so that this inequality is preserved. But we also have to preserve that we have neutrinos lighter than the cosmological constant. So the only scanning that seems to be in agreement with all three conjectures is the scanning with alpha equals 4. So putting all of this together, then non-AdS plus the anti-de Sitter distance conjecture, we have that the mass of the lightest neutrino is bounded from above. And if we also include the other conjecture, then not only the masses of the neutrinos are bounded from above, but it seems like the only scanning allowed, and we can find agreement with all of these conjectures, is a scanning where the cosmological constant also goes to zero. So perhaps neutrinos are the tower, because the cosmological constant is going to zero, and the neutrinos are linked through these conjectures. Now, for the last 2 minutes, I want to consider the possibility that our universe is not actually described by a de Sitter vacua, but instead by the quintessence runaway. Because if this is the case, then all we have said up to this point doesn't really apply, because it was all based on the assumption that we live in a vacua. So what happens to neutrino bounds in this case? So very briefly, turns out that if you use the de Sitter conjecture, you obtain similar results. But if you want to get the same bounds on neutrinos, then you need to apply a version of the de Sitter conjecture which also applies at anti-de Sitter vacua. This was argued in the literature that the quadratic version, where we include an absolute value, should also be true. And we also assume that the refinement for the de Sitter, at least for the de Sitter, it is not so clear that the refinement should apply for anti-de Sitter, at least not clear to me. So if we do this, and I will not have time to go into detail about this, but if we do this, we find that when we have minima along the radiant direction, which are the minima that we were studying before, we can violate the bound, but the result will depend on the C that we choose for the de Sitter conjecture and the CV, so the slope roll parameter for a particular quintessence potential. So if we use cosmology data, it was argued that the first part of the de Sitter conjecture can be made okay as long as the slope roll parameter is smaller than 0.6. So let's just say the results for 0.6, although our results would not change much. But if you want to obtain a particular bound, then you need to fix C and to fix CV. So assuming that CV is as small as allowed by C, so we both are 0.6, we find this bound. So that the lightest Dirac neutrino in normal ordering has to be smaller than 6.5 millielectron volts. And inverse hierarchy requires 0.03, and pure Majorana requires the C from the de Sitter conjecture is more than 0.002. So this strong tension we would point out to the fact that the neutrinos should be Dirac and in normal ordering. Okay, so this is my last slide. Some conclusions. So we have obtained similar upper bounds on neutrino masses from different Swampland conjectures. And for normal ordering Dirac neutrinos, we find that the total mass has to be more than 0.07 electron volts, and Planck's 18 bound is 0.12. So we see that we're very close, and it is expected that this bound will be lowered in the next 20 years. So this is interesting stuff. Also, perhaps the simplest seesaw explanation of why active neutrinos are so light seems inconsistent, and we should turn to quantum gravity for a deeper explanation of why neutrinos are of the same order of the cosmological constant, like perhaps they are part of the tower or somehow they are. That's it. So thank you all for listening.
All right. Thank you, Eduardo, for the very nice talk. Let us all thank Eduardo with our clap emojis. Are there any questions? While we wait for other questions, let me ask. Let me just ask about the assumption of the stability of the non-SUSY AdS vacuum in the first part. How strong of an assumption is this? I mean, can you provide some motivation that, I mean, one possibility is that this is just detecting that there should be other modes that you missed upon circle compactification that would provide instabilities. So can you say more about which direction you think that should go?
Yeah, I totally agree with you. I mean, if the conjecture was based only on that, an easy way out would be to like one of the ways out that you mentioned. And I don't have an argument why, in general, this vacua would be unstable. So we just consider a pretty generic setup, and since the same result is obtained from different angles, we propose that perhaps this is a more general feature, but more evidence perhaps from examples is necessary to take this seriously. So that in spirit, I agree with your, question.
All right, thanks. Oh, hey buddy, mommy's downstairs. I'm not sure, can you go check? Papa's empty. Sorry. Okay, and let me ask one more, let me shut my door real quick. Let me ask one more question as well. So these would be nearby AdS vacua in the standard model. Are these dangerous in any way? Like what is the estimate for the bubble nucleation rate to these nearby AdS vacua if you assume they exist?
Sorry, my audio cut it in the middle of your question for a while. So you're asking why is it dangerous that we have a non-anti-de Sitter, non-supersymmetric anti-de Sitter vacua in the standard model?
Yeah, near to our vacuum. I understood from what you said that there were some, depending on the masses of the neutrinos, there could be nearby AdS vacua that one could potentially tunnel to. I was just curious if there was anything dangerous about having these things nearby, if there was what the estimate for the tunneling rate to these was.
So our idea is that those vacua are not there. Mm-hmm. So that's precisely our argument, that they have to, according to quantum gravity, they cannot be there. So we want to forbid them. But I have not stopped to compute the possibility of tunneling to those vacua.
Got it. Okay. I was thinking it's probably a super low rate. Someone's surely has done it, but it would be really fun if there was some reason they shouldn't be there, and quantum gravity was confirming it.
Yeah. Perhaps there, in the literature somebody stopped to make numbers, because this was already known a few years ago. So
okay.
Cool.
Okay. Well, if there are no further questions, let us thank Eduardo for the very nice talk again.
Thank you. So